So we're starting our chapter on light. We've finished waves and sound waves, so we'll be taking a look at light as waves, and light also has the property that acts like a particle as well. But the purpose of these videos is mainly to take a look at how we answer some of the questions that are in our textbook. So here are a couple, and I have put the formulas that we'll need for this chapter, not too many, down at the bottom here. So this first question, Earth is 1.5 times 10 to the 11th meters from the sun, and the speed of light is 3.0 times 10 to the 8th meters per second. How long does it take sunlight to reach Earth? Now, before getting too far in this chapter, we're going to want to go ahead and store the speed of light into our calculator. So you're going to look for that STO button that she'll put an arrow there. And just like we stored the universal constant of gravitation, we're going to store the speed of light, and this time though into the value c. So there I'll have that available easily because we're going to need that here shortly. So how long does it take sunlight to reach Earth? So we really don't need a new formula for this. This is a distance problem. So basically what we're going to do, and I don't know why that just did that, but let me take care of that. Deselect that. Okay, so anyways, is basically our position formula. XF equals XI plus VIT plus a half AT squared. And there is no acceleration. It's a constant speed of light. And our initial position we'll say is the sun, so 0. So we are going to go 1.50 times 10 to the 11th equals VI is our speed of light. I'm just going to write C because I'm not going to want to keep on writing that. It happens too often. And time. So to solve for time, I'm going to divide both sides of this equation by C. So I'll go to my calculator. I have 1.5 times 10 to the 11th. And I'm going to divide that by C, which I've already stored, and I get 500. So C equal, or not C, T equals 500 seconds. All right, well, let's see how long that is. So there are 60 seconds in a minute. So I'll do 500 seconds times 60 seconds, 1 minute. Let's see what we get. So basically taking that 500 and dividing by 60. And I get 8. So 8.3 minutes based on the information in this problem. All right, so the next part, the star closest, I'm going to hide the formulas for now. The star closest to Earth besides the sun is 4.1 times 10 to the 6 meters. How long does it take us Earthlings to see the light from this? So basically it's going to be the same thing again. I'm not going to rewrite that formula. So it's 4.1 times 10 to the 16th. It's going to equal our velocity c times time. So I'm basically going to take that 4.1 times 10 to the 16th. And I am going to divide that by c, our speed of light. And I get a rather large number here. So let's see here. I see, we'll say that's 7. So 1, 3, 6, 6, 6, 6. How many sixes are there? I can't even see. A lot of them. I want to get that all down. 1, 2, 3. Oh, I'll probably screw it up, but that's okay. So that's in seconds. So that's not an extremely useful number right there. So let's change it to minutes. So I'll divide that by 60. That gives me minutes. And I'll divide that by 60 to give me hours. I'll divide that by 24 to give me days. And then let's see here, days. I guess I could do years next, so divide by 365 to give me years. All right, so it takes about 4 years for that light to get here. So that means actually, in a sense, that when you're looking at the night sky, in a sense, you're looking back in time, because the events that you're seeing in the sky have happened in the past by the time that the light has reached us to show us those events. Okay, so we have sent various spacecraft into space. So we do communicate with those spacecraft, and we do get signals from them. But what's the delay in that? Like, and this is something especially important. Like, if you were controlling the robots that are on Mars, there is a definite delay between the signal that we get from Mars and the signal that we send to the robot that's on there. So Voyager is going to be an extreme case because we actually sent that to leave our solar system. So the question here is, how long does it take a signal from Voyager to reach Earth? So it's essentially the same thing as what we just did. We are going to have this XF equals XI plus VIT plus a half AT squared, and light is not going to accelerate, and our initial position we'll say is Voyager, so is 0. So 1.8 times 10 to the 13th is going to equal the speed of light times t, and we'll divide by c. So the same basic idea. And I'm going to divide that by c and get 60,000. So t equals 60,000 seconds. Again, that's not very useful, so I'm going to change that to minutes. So I'll divide by 60 to give me minutes, and then I'll divide that by 60 to give me hours, and 17 hours. It takes 17 hours for that signal, so we're not going to be able to make anything but a very planned course correction, assuming that we can even control where it's going at this point. If it takes 15 minutes for a signal to get to a probe, how far away is the probe? Okay, so now we start with our time, but our time does need to be into seconds. So I'm going to multiply by 60 to get seconds. So 15 times 60. And we're going to get 900 seconds. Yes, our time unit is seconds for these equations. So same one as up there. So we want to know how far away it is. So we want XF. We're going to say Earth is the starting point, so 0. The speed of light is c, and our time is the 900. So basically, I'm going to take 900 and multiply it by c. And we get 2.7 times 10 to the 11th meters. So pretty far. All right, one more set. So if you read the chapter, which you should have if you are watching this video, the distances that we measure in space greatly imply that the universe is expanding, that things are growing further and further apart, and that's due to our observations of the Doppler effect, or in this case, what we would call redshift. So suppose a galaxy is observed to be moving 75,000 meters per second away from Earth. The light observed from this galaxy has a frequency of 5.6 times 10, and I don't know if you can see that, but that's a -7 power right there. What frequency of light did the galaxy actually emit? So we're going to take a look at our formulas here, see which one is most appropriate. So this first one is going to be the one that we want because it's basically the light version of the Doppler effect. And the thing that's changing is really down here. Instead of having the speed of sound, we're going to have the speed of light. because of the properties of light, it doesn't matter whether the observer is moving or the source is moving, and that's something that we'll see later in our chapter. So we really, unlike sound, we only need one formula. So for the redshift. So our observed frequency is this 5.6 times 10 to the negative 7th. That's going to equal our emitted frequency, or source, your book probably uses an FS there, times 1. Now I actually do forget, so let me look it up in our notes, which way it needs to go. Let's see. Plus for approaching, minus for moving away. So minus the velocity is 75,000 divided by the speed of light, c. Okay, so I'm going to do all of this quantity right here. So that's going to be 1 minus 75,000 divided by the speed of light. And this should give me a rather small number. Okay? Yeah, not much. Very close to 1. Now, we're going to have that number, and we're going to actually have to divide by that number. So I'm going to have this 5.6 times 10 to the negative 7th. And I'm going to divide that by the answer I just got. And we get 5.6014 times 10 to the negative 7th. So not a big difference right there. And suppose the galaxy was actually moving toward Earth. Well, then it's going to be the same thing, except we're going to have a plus right here. So I'll have the 5.6 times 10 to the negative 7th equals Fe times 1 plus 75,000 all over C. Nope, I don't want that. So I'm actually going to put this all in at once. So we're going to have 5.6 times 10 to the negative 7th. And we're eventually going to have to divide that by the quantity on the right side of the equation. So I'm going to type that in. And the right side of the equation is 1 plus 75,000 divided by C. And make sure I have that. Yep. Okay, and this time we get 5.5986 times 10 to the negative 7th for that. All right, that wraps up this section.